All right, welcome to another Marcialis Math moment. Similar triangles, right triangle addition. We're going to revisit the angle-angle similarity postulate. We're going to show how the altitude of a right triangle creates three similar right triangles. And then we're going to use similar right triangles to solve for the missing side. So, here we got two right triangles. ABC is a right triangle. Also, XYZ is a right triangle. Now let's take a look. We got the right angles labeled, and then we have these two acute angles that are corresponding, and they're both labeled 50 degrees. So I can say that angle C is congruent to angle Z. Now, let's look at the right angles. All right angles are congruent, so I can say angle A is congruent to angle X. Now, because if you pick either one of these triangles, I know two of the angles. I got a 90 and a 50. And so using the third angle postulate, I can figure out what the third angle is because the interior angles add up to 180 degrees in a triangle. Same thing with the right triangle, it's no different. So angle B is going to be congruent to angle Y because the leftovers in each of those triangles is 40 degrees. So my two right triangles are similar, right? That was the angle-angle similarity postulate that we talked about before, when we were talking about general cases of just any triangle. It's true for any triangle. It's easy to recognize in a right triangle because you really just need one acute angle, because two right triangles already have one angle in common that's congruent. That's the right angle. All right angles are congruent to each other. So you just need one acute angle in each triangle that corresponds that is marked congruent. So remember, similar triangles are the same shape, not necessarily the same size. So here I got my big right triangle ABC. It's outlined in pink. And then I got two other triangles, the green one, AOB, and the blue one, COB. And those two other smaller triangles are created by the altitude, BO. So let's look at the big triangle, the big pink triangle, versus the medium green triangle. So I'm going to look for the right angle in the green triangle, and we'll just call that angle B. It's up there at the vertex B. And let's compare it to the right angle in the green triangle. Well, the right angle occurs at number 3. They're both right angles, so they're congruent, right? All right angles are congruent to each other. Let's find another angle they have in common. Let's look at the two acute angles. Well, right away, I'm going to look at angle A for the big triangle because I notice that it's in the same position as angle 1 for my green triangle. It's actually the same angle, I just labeled it differently to tell it apart because it's actually angle A is congruent to angle A, or 1 is congruent to 1. That's reflexive. So now I have two angles in two triangles that correspond, that are congruent. By the angle-angle postulate, those two triangles are similar. So now let's look at our big pink triangle and compare it to our small blue triangle, COB. Well, let's write the triangle symbol there. So again, we'll start with our right angle. That's angle B, if we remember, for the big pink triangle. And the right angle for the little blue triangle is angle 4. Those two are congruent because they're both right angles. All right angles are congruent. So now we need to find an acute angle that corresponds in both triangles. So that's going to be angle C and angle 6. They're in the same position for both triangles. They're congruent because it's reflexive. It's the same angle. We just showed that these two triangles are similar. Well, if the big pink triangle is similar to the green one and the big pink triangle is similar to the blue one, well, by the transitive property, the green triangle is going to be, I said congruent, I meant similar. Ugh. By the transitive property, the green triangle is going to be similar to the blue triangle. So all three of those triangles are similar to each other. They're all the same shape, different sizes. So we can use that fact to solve for a missing side in a triangle. So here we have a right triangle ABC, and we have these two lengths down here. AD is 4, DC is 6. And we're looking for the height of the big triangle, big blue triangle. What's the height there? Or the altitude. We labeled it H for height. Well, because they're similar, I'm going to use, I like how I wrote use the blue and pink triangles, but that's not what I'm going to do. I'm going to use the green and pink triangles. That's a mistake. Because I go ahead and I draw the small green triangle, and I draw the medium-sized pink triangle, and I just leave the blue one alone. So yeah, I have the small triangle. I label the legs there. I have H as that horizontal leg, and then 6 is my vertical leg. And then I draw my pink or I draw the other triangle, and I got 4 as the horizontal leg, and H is my vertical leg. And I'm going to use these pictures to help me set up my proportion. That's how we solve, how we use proportions to solve for missing sides in any similar triangle. So I cross multiply, gives me 24 equals H squared. That's a messed up 2, sorry about that. Take the square root of both sides to solve for H. And I get H equals the square root of 24, which is 2 times the square root of 6. Final answer. Simplify those radicals, people. So, let's recap. We revisited the angle-angle similarity postulate. We just need 2 angles in 2 triangles that correspond to be congruent to show they're similar. And in right triangles, we actually just need 1 additional acute angle. That's it, because the right angles are already congruent. So it's pretty handy. We showed how the altitude of right triangle creates 3 similar right triangles. That altitude has to come from the right angle vertex to the opposite side, which is the hypotenuse. And then we use similar right triangles to solve for the missing side lengths of parts in those 3 similar triangles. Going to make sure we remember how to set up our proportions. When in doubt, draw a picture. Even if you label the picture wrong and you call it the blue triangle and you don't actually use the blue triangle, drawing the picture, I drew the picture correctly, and so it helped. Right? So we use the sides to find the height, or we can use the height to find the sides. I hope this helps.